So we're recording now. That's weird. The recording button looks different. Let's hope it's works the same. Okay. So let's get that whiteboard. You'll also hear my dog panting. He's extremely tired. I have no idea why. All right, so you should be able to see the screen. So I'm going to start on homework 13, EGL HGL, because it's one of my favorite questions ever. We're going to do two of my favorite questions ever today. So this is homework 13, EGL HGL, and this is number 4. Okay, so if you want to see the, if you want to like go back and look at the original. So the first part, this has got multiple parts, so this is going to take a little while. It actually won't take that long to work, but there's just some things that I think kind of get lost in this course, get lost in the shuffle. So when I found this problem, I was like, this is good. Okay, so it says water flows through a 2-to-1 diameter pipe contraction as shown in the figure below. So we've got a pipe and it's contracting. Okay, and it's a 2-to-1 diameter, so this is, whatever it is, this is twice as big as that. But in this case, it says this one is 0.1 meters. So without doing a whole heck of a lot, we're just going to know that this is 0.05 meters. Okay. The large section of the pipe upstream has a diameter of, okay, a pitot tube is installed in the large section of the pipe, and a piezometer is installed in the small section of the pipe. So this is a pitot tube. Looks like this. Okay. I mean, obviously, I'm just not going to erase that little bit there. And then there's okay, so this is a piezometer on the right, and the pitot tube is on the left. The difference in height between the pitot tube and the piezometer is 0.2 meters. So basically, there's a surface here, and there's a surface here, and this distance is 0.2 meters. Okay, so the first thing, this thing is broken up into a lot of parts. So we've got I and I. And they want to know the velocity of flow in the small section. So if we call that small section, like, I don't know, section 2 or something. So if we go, this is section 1 here, and this is section 2 here. They want to know what is V2. And then they want to know Q. Okay, now we're not going to bother with Q because I have other, well, we'll go ahead and do Q. It won't take all that long. Any thoughts on how to get at this?
So I mean, we did these problems before with like the stagnation, right? It's like the difference in height is equivalent to the velocity squared over 2g, right?
Yeah, the problem, of course, is in this case, what we're not doing is we're not at the exact same location. So if this was like this, and we had this and and this, then the difference in height between these two would be exactly v squared on 2g. Because the flow conditions, like this is like one streamline, and there's no difference between the flow conditions here and here and here. Well, this is a stagnation point, but other than that, there's no flow difference along that streamline. So the only reason the water has been driven up higher here is because of that stagnation. But in this case, the problem is that point 2 is at we have a narrower pipe, so we can't necessarily do it that simply. But that's the right idea. That's exactly the right idea. So basically, what it boils down to is, so if I did the energy equation from 1 to 2. Okay, so well, not the energy. I'm going to do Bernoulli, and the reason I'm choosing Bernoulli is because I'm going to assume that there's no energy loss between 1 and 2, which they're really close to each other, so that should be pretty reasonable. And then obviously there's some energy loss, but it's just not really all that much. So what we do here, you've got the right idea, is that so the Z's go away, right? Because there's no height difference between these two. But what we can do is we can say for this location right here, for location 1, all of this, because the shape of that, because it's a pitot tube, all of this is P on gamma plus V squared on 2G. So P on gamma goes up some height in here, and I don't know where it is exactly. Let's say it goes up to here, P on gamma. And then the rest of this is V squared on 2G, right? So I don't know where this point is, right? I'm just kind of making it up, right? But regardless, I know that this distance right here, H plus 0.2 meters, whatever that total distance is this plus this. Does that make sense?
I think so. I think so. So you're saying it's like it's the same, but it'll be since it's a smaller pipe, right?
Wait, yeah, I'm only looking at the larger pipe at the moment. So basically, like if I had like in this situation right here, if I look over to the left, right? So I've got a P on gamma. So if I had put this tube right here, instead of here, I'd put it right here. So I've got an open tube going down to the bottom. Then the water in this, or whatever the fluid is, would have risen to here. So this height right here would have been the pressure in the pipe. And then the extra bit that it rose would be V squared on 2G. Okay, and that's because of stagnation. Does that make sense?
Yeah, I got you.
Yeah, so we're doing the same thing over here. I just don't have the extra pipe.
I got you. And so then that equals H plus 0.2.
Right, so we can take this left-hand side, the whole left-hand side, and make it H plus 0.2 meters. And I don't know what H is, but well, H is a distance from this center line, which should go through both of those points, and this spot right here. And then I can go over here and I can say, well, P on gamma, P2 on gamma, well, that's exactly what the piezometer is designed to measure. So that's H. And then we have V squared on 2G. And so what ends up happening is actually, I guess you were exactly correct with your first guess, is that, these H's go away. I'm left with V squared on 2G equals 0.2 meters. Right, so we can solve that pretty easily. I guess algebraically, I'll plug that in real quick. Let's see here, 0.2 times 2 times 9.81. Take the square root of that. So V equals 1.9809 meters per second. And then Q equals that number times the area. I'm not going to do that part. Okay, you know how to do that. Okay, we just multiply that times pi times 0.05 meters squared divided by 4. All right, that makes sense? We cool?
I got you.
Okay, cool. So one of the reasons I asked this question, or one of the reasons I love this question, is I saw this on an FV. I don't remember if it was an actual FV or if it was a review for the FV, but they just had, the problem was really quite simple. And it was this problem right here, essentially. But it was one pipe. So basically it was what we see on here on the left, on the right. And all they did, I think, was I didn't mean to erase. They drew, why do you keep erasing? I'm selecting the non-eraser. I know you can hear me selecting. Maybe if I choose a different color, it will know that we're doing something different here. Oh. Okay, can we get, okay. Give me black. All right, so yeah, so basically the problem looked like this. And I think these two things were connected even. Can't remember if they were connected or not. And the only thing they gave you was this height difference between the two locations. And I kept staring at that and wondering if my students could do it. Not that they couldn't do it, but if I had prepared them for that question. And so that's just, where I really loved this one. All right, so the second bit of this one, okay, we're not going to get Q. I'm assuming you're okay with me not getting Q.
Yeah, that's easy.
Okay, right. At this point, that's my hope. At this point in the class, you'd be like, yeah, I got that. Okay, so, and the nice thing about these tubes, and that's kind of what I wanted to point out with this question, is that these tubes, they give you, they like plug directly into energy or Bernoulli. So whenever you see one, you should know exactly what you're working with. I mean, as long as, if it's a piezometer. Now, if it's a manometer, that's a little bit different. But all right, so this one looks like this. Come on. What is wrong with you? I have no idea why it's doing. Why would you do this? Okay, there you go. All right, so second one looks like this. I mean, it's the same problem, but instead we've got piezometers at both locations, and it doesn't give you this height here, H. And it says, you know, it's the same situation. So we've got 0.1 meters, and this, of course, is 0.05 meters. I know it's a sloppy drawing. And it asks you to solve for H in terms of the flow rate. So H equals H as a function of Q. Okay, that's the first problem. And then the second problem is to solve for H if Q equals whatever it was in the first part. So we're not going to do that because we know how to do that. Come on. All right, we're going to try to erase as little as possible. It seems to really love the eraser this morning. Doesn't want to let me do anything. Okay, here we go. Okay, so so here what we're going to do is, you know, we need H as a function of Q. So we kind of need H as a function of velocity. So we're going to do the same thing we did last time, plus, let's see here. So Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. Okay, so again, those Z's are going to go away. Seriously? I didn't even hit eraser. Okay, so the Z's are going to go away because they're the same. The velocities are not the same. And P1 on gamma versus P2 on gamma, I just know that P1 over gamma is this distance, and P2 on gamma is this distance. And so the difference between those two is H. Okay, so I could say, you know, P1 on gamma minus P2 over gamma equals H. Or if that's like confusing, we can always do, you know, this distance right here is maybe capital H. And so I could say, okay, well, P1 on gamma is H plus H. P2 on gamma is just capital H, right? And then I just got to get V1 and V2, because what I'm looking for is H as a function of Q. So right in here is where my Q is going to come in. And so really the ideal way to solve this, if you wanted to get it to come all the way out, is instead of, you know, now normally what I like to do is I like to look at this and go, okay, well, V2 is going to be 4 times V1. You know how I got that, right? You're okay with that?
Yeah, that makes sense.
Okay. So normally what I like to do is I like to take that and plug it in over here, right? For plug it in for V2. And then that way I can solve for V1. I'd be able to solve for V1 in terms of V2. But if you look at around the internet, you'll see, because most of the time with these problems, what we're solving for is Q. And that's kind of what we're doing for in this case. We're not really solving for Q, but we want to plug Q in. And so what we want to do in this case is actually instead for V1 and V2, what I want to plug in is I want to plug in, let's see here, I want to do V1 equals Q over A1. Because this way, if I plug that in instead, Q is going to be in my expression and I'll be able to pull that out. And V2 equals Q on A2. So I can solve that, well, I can quote unquote solve those. If I say V1 equals Q over pi over 4 times the diameter at A1, which is 0.1 meters squared. And V2 equals Q on pi on 4, 0.05 meters squared. Okay, and so this is going to be a really ugly number. But if you look around the internet, a lot of people will solve these problems by plugging in Q. I don't like to do it because it creates all kinds of ugly powers. Like if you take this, for example, with just the D in there, and you plug it in up here, you end up getting, you know, D to the 4th on the bottom of the top, if that makes any sense. And so ultimately it ends up in the denominator. And students forget to bring things to the 4th. I say students do that. I do that. So I don't want to, malign my students. But yeah, so what we'll do is we'll say, okay, well, pi over 4, pi divided by 4 times 0.1, we'll square it. Okay, and we'll put that on the bottom. Oh, not like that. Okay, and we'll get 127.32. So this is 127.32 Q. And V2 is going to be, well, V2 is 4 times that, right? So we'll take that number and multiply times 4. And we'll get 509.30 Q. And there's some units in there that I'm ignoring at the moment. But what's interesting, first of all, is to see these massive numbers and to go, wow, that's really big. But remember, these diameters are really small. 0.5 centimeters and 10 centimeters is, pretty small pipe. And we're trying to get units in terms of cubic meters per second. So it's going to be pretty small. So what we'll do is we'll plug those in. And so I'll get 127.32 Q here. And I've got to square that and divide by 2G. And I've got to do the same over here, 509.30 Q. I need to square that and divide by 2G. And so what we'll see here is, these capital H's go away, as could only happen. And then we just have to solve this, So actually, I guess we've already solved it, really. We just bring this over to the other side, square and subtract. And so I'll end up with H equals, let's see here. So we'll do 509.30 squared. And then I'm going to subtract out 127.32 squared. And I'm going to divide by 2 and divide by G, 9.81. And I get this massively ridiculous number. H equals 12394 Q squared. Okay. Now I have to remember the units, which I kind of forgot about here. So this had a, let's see, so right in here, there is a per meter squared. So there's a meter squared on the bottom. So if I go into here and I square that, I get meters to the 4th on the bottom. But then that got multiplied by, but the bottom had a 2G on it. Right, so those G's is meters per second squared. So this is seconds squared, and that's meters to the 5th. Okay, and that makes sense because if I plug into Q, if I plug in meters cubed per second, and I square that, then I get meters to the 6th per second squared, and it all cancels out except for that 1 meters. So this is our answer. And of course, this is definitely something that you might want. In fact, I think probably more often than not, like if you had this sort of setup, you'd probably want it to go the other way, right? You'd actually want to solve this as Q equals the square root of H over 12394, and then out front meters to the 5th over seconds. Because what you would want to do is you'd want to be able to walk up to this thing, read H, and just divide by 12394, and then take the square root, and then you get your Q. And you're like, okay, the system is running as it's supposed to because we needed a flow rate of whatever. So that's the idea of it, as sloppy as this work is. Does that make sense? I know it's really sloppy work.
Yeah, it makes sense.
Okay.
I mean, what I would have done is like done the algebra more, or would you advise like turning it into numbers?
Oh no, I do not advise turning it into numbers.
Okay, so if I can do it, I should just do the algebra all the way out, and then.
Yes. I do algebra more than I'd like because many of my students prefer that. In an ideal world, you would use the variables all the way to the end. You wouldn't put numbers in until the very end. Because all the rounding errors, I mean, the reason I even have to come up with rounding rules, like keep at least 5 digits, round to 3 at the end, is usually because my students like to plug in numbers as soon as they can. And I remember doing that when I was a student too. And then when I got to grad school, I kind of started, I remember my professor saying to keep variables, and that just seemed like such a pain to me, but it is the best way to do it. Absolutely, unquestionably. So yeah, absolutely.
Okay.
Do it that way. Also, that way, like a lot of times the variables will cancel out, and that makes your life a lot easier, and you can see the relationships a lot better. So, like when I'm staring at this relationship right here, I'm kind of like, does that make sense? I don't know. It just seems, weird, so yeah. So anyway. All right, so let's do this last one here. Let me clear all. Okay, and the last one is basically a third version of this. Now the second piezometer is swapped for a pitot tube. Okay, so now we've got, come on, you can do it. Okay, yeah, so same situation. We've got a pitot tube here. Okay, we've got a piezometer here. Okay, and this one is higher, and this one's lower. Okay, by some distance h. Okay, again, we're assuming that I'm a better drawer than I am. Okay, so we want, so that's given. Okay, same setup, 0.1 meters. And let's do it your way. Let's just use symbols here. D equals, this is 0.05 meters. Okay, an expression for the difference in the fluid and piezometer, and pitot term H in terms of the flow rate. So required. H equals H as a function of Q. Okay, so we're not going to do we're just going to do that part. Okay, so again, gamma, or not gamma 1. That would be very confusing. The nice thing about this problem is it becomes like fairly simple once you start to see what it is that you're doing. Okay, and so once again here, we're going to get rid of the Z's because it's on the level, like this is our datum. Or you could have any datum and you could just say, well, they're the same. And then for, P1 on gamma, well, that's this distance right here, which we don't know. I could call it capital H if I wanted to, which wouldn't really be necessary. So I'm just going to note that, P2, well, yeah, let's just keep it in one place. So we're going to call this H plus, and then we've got V1 squared on 2G, but we need an expression with Q in there. So this is going to be Q. So V1 is going to be Q on A. Q on A, which in this case is pi over 4 times D1 squared, right? And then we're going to go ahead and square that. Okay, so I don't like that. That's why I usually solve for V1 first and then go get Q. But that to me is just like, with all the fractions and things, it's just kind of, in squaring, it just asks for a careless error. But anyway, but then on the right-hand side, we've got P2 on gamma plus V2 squared on 2G. And that, of course, is all expressed in this distance because it's a pitot tube. So that's going to be H plus H, H plus H. Okay. Questions? All that's fine. Oh, I'm all alone. Am I all alone? No.
That sounds.
Okay. Yeah. Sorry. It was only showing me. Let's see here. Can we get the gallery people? Oh, hey guys. Okay, so we're going to take those H's and we're going to cross them out, and then we've got so the algebra here, it trips me up a little bit. So I get Q squared. I know I've got 2G on the bottom, and I'm just going to kind of start figuring out where things go. So that pi is going to be on the bottom. That D1 squared is going to be on the bottom, but it's going to be to the 4th. D1 to the 4th. That pi I forgot to square, so it's got a square on it. And that little 4 right there, which is on the bottom of the top, or whatever, it's going to become a 16 out here.
Dr. Wagner,
Yes, sir.
if you got on a B1, you got a pi before, and on B2, you eventually gonna have pi before. Can they cancel each other out?
If every term in the expression had a pi over 4, then yes.
So like you can't cancel out even like because the p's and they don't have the pi before, you can't cancel out those
Right.
two.
Right. Right. And in this case, we didn't end up with the pi over 4 because we didn't plug in here, because we noted that this whole quantity right here is a vertical distance equal to from here to here.
Yeah.
So that was just an easier way to solve it.
All right.
But all of this we set equal to h. Okay, and so that's the solution to this problem. Okay, and it's super ugly, but you know, I mean, staring at this is one of those things where when you get this one, for me, it's like take an extra 30 seconds and just make sure you're doing it right. It's not impossible, but it is something if you're rushing, at least for me, I'll make that careless error every time. I'll forget to square something. So I'll leave the pi on top. Sometimes I'll just even forget a whole term and like I'll just forget to recopy the pi. You know, or usually that 4 stays a 4 and doesn't become a 16. So, and then of course it's moments like this where this is where I check my units usually to make. I mean it's a fairly quick thing. So I've got q squared. So that's meters cubed over seconds squared. Over what I want to do is make sure that all of this gives me a meter right here. And so G is meters per second squared, and then D to the 4th is meters to the 4th. So I've got meters to the 6th over second squared on top over meters to the 5th over second squared. So we look good, right? So that's just a check. If you get that, then you should feel pretty good. You know, I mean, obviously, you know, the pi doesn't have units, the 2 doesn't have units, you know, the 16 doesn't have units, so you can still screw it up, but you know, usually that's a pretty good sign. Checking units is a skill that we don't really emphasize enough, but if you do it and if you do it right, then you know, things usually work out for you. It's a good habit to get into. The second part of this problem, if you look at it, is just like, you know, what is the h given the q from the earlier part of the problem? So that's just plugging numbers in with the calculator. Anyway, if you feel like going to go look at that problem, you may, but it's not really necessary. Okay, so we're going to clear all drawings. And then we're going to do one more. So this one we're going to do, hold on, let me, is from, this is another one of my absolute favorites. So this is homework 14. So this is right before you get to the videos that we're about to do. But this will be like the last HGL EGL. This problem has everything, except it doesn't have all the losses. All right, so this is homework 14, and this is number 2. And I would recommend pulling it up on your screen just to look at, because it's not easy. I asked for a lot of things on it. And so it's going to take me a couple seconds to draw this. I'm actually going to get out my ruler so that it comes out pretty neat. Because otherwise it's going to be really difficult to understand what's going on here. It's not going to be perfect or anything, but it's going to be neater than my other drawings. Okay, so now we've got a pipe that's 300 meters long. Let's make it 12 centimeters according to my ruler. Okay, sound effects are always important. I highly recommend them. Okay, and then it's gonna turn from there. How far is that one? 100 feet. So if that was 12, this needs to be 4. Okay, we're gonna assume this is the same diameter. I know it doesn't look it. And then we got 30 feet, which I'm not gonna make to scale because I don't care. Okay, and then we've got another reservoir down here. So we talked about this one, I think, ever so briefly. You know, I kind of drew it and I was like, where do you think it would cavitate? But we're going to go a lot more in detail on this one. And hopefully I have enough space to do this. I'm probably just gonna have to keep erasing on the bottom here. Anyway, so down here at this lower reservoir, I'm gonna put the elevation of the water. I'll probably move it at some point. So, you know, if it'll help me with the drawing, then I'm gonna move the elevation of the water. It's just there for now. So the elevation is 100 feet. Okay, the elevation over here is unknown. Let's make that blue too. Okay, so go like right here. Okay, it's a little bit above or whatever. Now this, I like this problem because I could almost like make this the whole final. I mean, obviously I'd have to find, you know, it would need a few more pieces, but it basically covers almost everything we would want to know, or everything towards the end of this semester. So elevation question mark. Okay, so this distance right here, this is 300 feet. This is a 100-foot section of pipe. And this is a 30-foot section of pipe. Okay, this elevation right here, that's 40 feet. This little bit, yeah, I mean, everything that looks horizontal is horizontal. This bit right here, this is 45 degrees. This is a diameter of 1 foot. The whole pipe has a diameter of 1 foot. This is water at 50 degrees F. And oh, the last thing they tell you, and if you haven't watched the videos, you won't necessarily know what this is, but F equals 0.025. Okay, it's never going to be that simple for you to get F. If I give you F, it's because I just wanted to say like, hey, can you use the energy equation? But getting F is kind of one of the big challenges of this course. And so every problem after this one, we will have to go find F. You have to get it off the Moody diagram. It just so happens in this case that they give you F. Okay, so we're gonna, maybe I'll put what we want up here because there's a lot of them, A through F. A, B, C, D, E, F. Okay, A. Q equals 20 CFS. Okay, so then what is Z1? So Z1 equals what? Now we'll go ahead and put point 1 right here. Okay. For B, we want HGL EGL. Now we're going to do that quantitatively for this one. When I wrote the instructions for this, I told them to plot a point every 50 feet. It's really not that, it's easier to do than that, and we'll do it the easier way. Okay, C, where is minimum pressure in the pipe? Okay, so P min is where. D, what is the magnitude of the pressure at that point? P at, let's see, oh no, let's see. Yeah, I guess P equals what at X where P equals P min. That's a pretty roundabout way. Okay, so basically what is the pressure at the minimum pressure? So P min equals what? I guess is what I should have put right there. Hopefully this isn't so small that you can't see it. Let's see here. E, will water cavitate? Okay, and I like to ask that question. Almost always the answer is no. I have to like kind of really engineer the problem to make it cavitate. Well, I guess it's really not that hard to engineer. It's not like it's a lot of energy to do that, but it's just that I want you to make sure that you guys know how to do that. And then the last thing is, what kind of pipe is this? Okay, and we'll get into how to do that, because if you haven't watched the video, you have no idea how to do that. So the most quantitative part of this whole thing is A. So we're gonna go ahead and do that, and then we'll just erase our work. I'll try to remember to save what it is that we need from that. But the first thing we're gonna need, and I'm gonna do this as an aside, is if Q equals 20 CFS, I know I'm gonna need V. So V equals what? Well, let's just start with the energy equation. P1 over gamma plus Z1 plus alpha V1 squared on 2G plus HP equals P2 on gamma plus Z2 plus alpha V2 squared on 2G plus HT plus the head loss. Okay. Now I'm going to note again that there is head loss that we are not going to account for in these minor losses. Okay, and the minor losses are the last thing that we will cover. But we're not going to worry about those just yet. Okay, so next up, let's see, hold on. Okay, next thing, I like to get rid of the easy things. Between 1, well, we have to pick where point 2 is. This is the obvious point because it's the easy spot, right? So what is our datum? Well, to me, the datum, if they give us elevations, I just like to use the elevations rather than to change them. So the datum is at z equals 0. Okay, so that means that Z1, this is what we're looking for. Z2 is going to be 100 feet, okay, because that's given. Okay, and then we have no velocities. Velocity 1 is 0, velocity 2 is 0. That's nice, right, because they're reservoirs. Okay, reservoirs or the tank assumption.
Is that always though?
It is. You mean, is that always 0?
Yeah, 0.
You mean the V or the Z?
The V's.
The V's are zeros because my points are right here. You know, it's on the top of a reservoir.
Yeah.
Top of a reservoir. So as long as it's on top of a reservoir, then the velocity is 0.
All right.
Okay. All right. So then
Are
between
the P's 0 too?
Yeah, the P's are 0 too. Yeah, I'm kind of a little scatterbrained right now, but yeah, you're right. The P's are 0 because those are atmospheric. Okay. We don't have a pump between number 1 and number 2, so this goes away. We don't have a turbine between 1 and 2, so that goes away. And we've just got this head loss. And this head loss gets split out into the head loss due to friction and the head loss due to like minor losses. And of course, in this case, we don't know how to deal with the minor losses, the ones in yellow. So we're just going to get rid of those as well. Okay. This is what we call, this is like, you know, a very simple model of like, for example, irrigation in California. What happens is, you know, or in a lot of places really, is this is a gravity fed system, basically. You have water at a higher elevation and you just let it run downhill to a lower reservoir. And usually in between these two spots, if this were California, first, it wouldn't be 300 feet, it would be 300 miles or whatever. But in between those spots, you'd have farmers taking water out, taking water out, taking water out, or you'd have a city taking water out. The key is getting the water to the higher elevation. Once it's at the higher elevation, you're good. So either you have to pump it to the higher elevation or it's rainwater that falls in the mountains and it already has that higher elevation. So anyway, so we end up getting, if I recopy this thing down, I end up with say Z1 equals 100 feet plus the head loss due to friction, HF. Okay. So this is just gravity fed, you know, irrigation or whatever you want to call it. Now, I always like this moment in the problem because I'm like, I feel very satisfied. Like, you know, this is just such a simple expression. Unfortunately, a lot of times, especially in these Moody problems, this is going to get, we'll do, if we have time today, we'll do a Moody. That is going to require you guys to pull out a Moody diagram, which you probably haven't done yet. But if you have a hard copy, I'll ask you to pull one out. If you don't have one, you should probably print one. And you should find one that you like and get used to using it. There's one.
Would that be in the FE thing that you gave us, like at the beginning of the semester?
There is a Moody diagram in that one. I don't necessarily love that one, but you know, that might be a good one to use. We'll figure that out in a second. Anyway, usually, like, I don't know. We can look into that in a second. Okay. So this HF, okay, the expression for that is, and this is always the case. Oh, come on. Okay, so it's F L over D B squared on 2G. Okay, now that expression will change pipe by pipe. So if we had more than one pipe, you would have to, you know, you'd have to add 2F L and D V squared on 2Gs if the pipes were a different diameter, or, you know, obviously they have different diameters, they're gonna have different velocities. But they will definitely have, they'll also have different Fs. They probably have different lengths, you know, all of that. So you'd have to split that out into two terms. In this case, we basically just have what it essentially boils down to a 430 foot long pipe. And that's one pipe. So we're not gonna stress out too much over, splitting it out. You could split this out. You could do F1, L1, D1, B1 squared on 2G for like this section, and then do plus F2 L squared on D2, B2 squared on 2G for that section, and then do the same for this one. Doesn't really make a lot of sense to do it that way, but you could do it that way. All right, so then what we'll do is we're going to solve for this. We need to know V. Okay, so over here, we're going to do Q. We're going to do Q over A to get our V. Okay, so V equals Q was 20 CFS over the area, which is pi, what's D in this case? 1 foot squared on 4. So V equals whatever that is. If I had a printer, I could just have this whole thing in front of me. 80 divided by pi. Okay, so we get 25.465 feet per second. Okay, so now we're ready. Okay, so we're just going to go ahead and solve this sucker right here. 100 feet plus F 0.025, that's given. Note the order of magnitude of this thing. This is a pretty typical order of magnitude for these. A big problem that happens on a lot of, or a big careless error, is people will put in 0.25, or they'll put in an extra 0. So when you look at the Moody diagram, it'll be clear about what the order of magnitude should be. So just be careful and don't have too many zeros. If you watch me work problems, I'm going to make that error too. So it's no big deal. So L over D. I'm actually going to do something here which is a little bit unusual. I'm going to separate those two. So what I'm going to do is I'm going to do 1 over D, where D is 1 foot, and I'll explain why in a second. It'll be obvious, or hopefully it'll make sense. Come on, man. 1 foot. Okay. And then I'm going to do V squared on 2G. I'm ignoring the L for a second. The V squared is going to be 25.465 feet per second squared over 2 times the G, which is 32.2 feet per second squared. And then I'm going to put this L out front. What is the L? L is the total, 300 plus 100 plus 30, so that's 430 feet. Okay, a question I commonly get from people is it only vertical distance? No, it's anywhere where the friction is acting. So the friction is acting along that entire pipe. So it's going to be that entire 430 feet. Notice that 100 of those feet are on an angle, but it doesn't matter if it's on an angle. It could be straight down. It could go backwards. It doesn't matter. All right. So I'm going to go ahead and solve this. Z1 is 100 feet plus, and hopefully I'm going to explain real quick in a second why I split that out. You don't always have to do it. In fact, usually you do not have to, but I do think it's helpful. Divided by 64.4. So I'm going to get 0.25173. Okay, and the units here, and that's going to be times 430 feet. Okay, the units for this number right here, this 0.25173. So that's all of this. Okay, and the units for that, if you look at it, we end up with feet per second, and then we square that over feet per second squared. And so we get feet from this, and we've got a per foot on the bottom. So the units for this are feet per foot. So, or no units, depends on how you want to look at it. But what that's telling us is we are losing this much head for every foot we go along those pipes, along that pipe. So we're losing 1/4 of a foot, or 4 inches, more or less, of head for every foot we go along that pipe. Okay, now I'm going to go ahead and solve this because we don't care about that, but we do if we're going to draw a detailed version of the HGL EGL, which we're going to do in a second. Okay, so we've got Z1 equals, let's see, so we'll multiply by 430. So that number times 430, okay, plus 100 equals 208.25. Okay, and that's feet. Okay, so as an answer, I would want 208 feet. Okay, so this elevation over here, so for part 1, equals 208 feet. Okay, now we're going to draw the detailed it's not even really that detailed, but we're actually going to try to figure out the HGL EGL, and we're going to do this quantitatively. And so that's where this comes in. That tells me this is the slope of the energy line. This is how much energy we lose per foot along those pipes. And since we're ignoring these minor losses, we're going to ignore this, we're going to ignore that, we're going to ignore this, we're going to ignore that. Since we're ignoring all of those, then that just tells us the slope between the two blue lines, basically. So my EGL looks like this. Let's see here. So my energy grade line is just a straight line between these two. Okay, that's the EGL. Okay, and then the HGL. Well, let's see. We could do that. Oh, well, yeah, it's a little weird. I really don't like not having any head loss at the exit, because really it shouldn't ever come like that. So just be wary of that this is, there should be an exit loss right here. Because without it, it's a little bit sloppy. It's very sloppy, but as we teach these things to you, it's usually how they do it. So anyway, so then we need to figure out, well, what's the difference between this line and the HGL? Well, the difference between the two of them is the V squared on 2G, which fortunately, well, I wasn't quite as proactive as I thought I would be, but that's this right here. So V squared on 2G, if I plug that into the calculator, let's see here. So that's 25.465, square it, divided by 64.4, and that's 10.069 feet. And so if I was doing this 100% to scale, and I knew what 10 feet were, it's not 100% towards scale, obviously, but I knew what that 10.07 feet were. I could draw this line exactly underneath this thing, 10.0 whatever feet, 10.07 feet below, like that. Okay, and this would be, I mean, it's a little weird to imagine this thing jumping right here, but anyway, so that would be our HGL. Okay, and what's cool about this is, again, like, so, we've got some elevation for everything. So, imagining I'm right here. Okay, here's my Z coming up from some datum. My Z goes to here. My P on gamma is here. So if I put a piezometer in here, right here, that's how high it would go. And then here's my V squared on 2G. And of course, that's pretty small, but V squared on 2G. Okay. And then we'll notice that the possibility for negative pressure does exist in one location. That's right in here. Okay, that's the only place where the HGL drops below Z. And that of course could be an artifact of my drawing, right? Because the locations of this elevation and this elevation, I just made up a spot, right? That's not to scale. So it may not go negative, it may go really negative. Like, if this line right here was supposed to be down here, well, then maybe the pressure there is really negative. But the nice thing here is, like, okay, so we've done the HGL EGL. Hold on, let's check that off since we're on to the next thing. We know where the minimum pressure is because we can just look at this and we can see where the minimum pressure is, because this is the spot where the HGL drops below. Really what we're looking for is, like, we're looking at this thing right here and we're going, okay, well, here's P on gamma, here's P on gamma, here's P on gamma, here's P on gamma. And then we're getting closer and closer and closer. And all of a sudden right in here, maybe it goes a little bit negative, before all of a sudden we're going positive again. Because what we're comparing is Z, which is the center of that pipe, to the HGL. Okay, so without doing any math, we can see where it's most likely to go negative, and that's right here. Okay, right at this kink. Okay, and what we want to do at that point is we want to say, okay, well, where is the P min? Well, we just identified that. And then we want to know, well, what is the P min? Okay, now there's two ways to do this. They're ultimately the same, but one of them is we can say, okay, well, we can basically figure out, so notice that all the loss in pressure is coming, I mean, all the loss in energy is coming due to pressure. So I can figure out kind of what the pressure is right here entering the pipe. And then I can basically subtract this much pressure per foot until we get to that point. Okay, that's a little weird. Okay, what's really going to be your better way to do it is to do the energy equation from 1 to this point right here. Okay, so we'll call this point star. Okay, luckily, we've essentially already done it. Okay, and I'm going to do it by doctoring this equation a little bit. So I'm going to go up here, and instead of Z1, I'm going to put 208.25 feet. Okay, we're going to be at star, so we're doing a point at star. The elevation is 100. Oh, well, sorry, we do have a pressure there. So let's just go ahead and let's just redo the right-hand side of this. Okay, yeah, I've got what I need below. Okay, so I'm going to do this kind of blue on top. We still have this term. Oh, come on. We still have P on gamma, P star on gamma. We have Z star remains 100 feet. We've got a velocity that we have to deal with, V star squared on 2G. And we've got a head loss we have to deal with here. Okay, so let me put in the intermediate step here. So we're going to say is we got, okay, so we've got P star on gamma. That's what we're looking for. Come on. P star on gamma plus 100 feet plus alpha V star squared on 2G. Luckily, V star squared on 2G we've already solved for. Plus FL on D, V squared on 2G. Now I'm going to make that same correction I made earlier. I'm going to get rid of that L. Come on. Just right. Okay, like that. I'm going to put the L out front. Okay, same reason as last time. And also I've already solved for that other quantity right here. So that just makes things a little bit easier. Okay, so the only trick with this whole thing is this alpha right here. I'm actually going to go back in a second and figure out if alpha. So what we're going to do right now, just because I don't want to deal with it right now, if you had this on a test, you should deal with it first. But we're going to assume that alpha is 1.0. We're going to come back and check that later. I can tell you right now it will be. This velocity is way too high, and the diameter of the pipe is way too small. It's definitely going to be turbulent, but we're going to check it in a second. I just don't feel like dealing with it right now. So P on gamma is what we're looking for. Okay, 100 feet. V squared on 2G is this number right here. 10, oh, not equals, plus 10.069 feet. And then this number, 0.25173 feet per foot. Okay, times the length. Now remember, that's the length from 1 to star, so that's 300 feet this time. Okay, and then this is just an algebra problem. And of course, gamma in this case, we always have to be careful with that. So in this case, gamma is 9810 newtons per meter cubed. Okay.
Don't we need feet though?
Thank you. Right, of course. 62.4. Yeah, it's amazing, like as I'm grading, I get really frustrated with you guys when y'all make that error, but I make that error too, It's like I'm looking at it, I'm like, oh, how could they still be doing this? And of course, I've been doing this for, I've been like specializing in fluid mechanics for like 15 years. and I still make that error. So this is a calculator moment. Let's go ahead and do it. Clear. Plus 10.069 plus 100 equals that number minus 208.25 times 62.4. Okay, so P at star equals 1414.1. Okay, and the units of that are pounds per square foot. Okay, and the key to this is remember that this is gauge, because the next question is they're going to ask, does it cavitate? And that's why they tell you the temperature of the water right here. Well, there's two reasons, that and to get the viscosity for calculating the Reynolds number up here. So I'm going to go ahead and convert that to absolute. What is the atmospheric pressure in PSF is, let's see, it's 14.7 times 144, it's 2116. So what we're going to do is, this is gauge, so we're going to add 2116. So add 2116. So we're basically adding atmospheric pressure here, 2116.8, and we get 4233.6 PSF absolute. Okay, and then to see if that will cavitate, I have this fancy chart here. Different books do it different ways. Some of them have, like, you know, a line graph, but this is the chart you need. You know, I'm sure, hopefully you figured that out by now. And so at 50 degrees C, oh, you know what? This stinks. It only gives you in KPA. All right, well, I'll have to remember that and give you all the question in, give you the question using the SI system. Anyway, what you would do is you would compare this if I knew what it was in PSFI. Usually it's going to be in PSI, so you'd have to convert this to PSI. But the bottom line here is it's not going to cavitate. And the way we know in this case, it's not even negative. Didn't even come out as a negative number. So if it's not negative, it's not going to cavitate. So you actually don't even need to check that chart in this case. But basically, if this pressure is below the vapor pressure, then it will cavitate. Okay. Last bit. What kind of pipe is this? Okay. And this is interesting because you at this point you have no idea how to get this, I'm assuming. Is that correct? You're like staring and going, I don't know how to do that.
I mean, I pulled up a Moody diagram after you talked about it, and I can see what.
So you see at the bottom, somewhere on there, it probably has types of pipe. Now, what the lengths on there, are they in are they SI or are they English?
It's a SI.
Okay, let's find one with English. Did you pull up the FE one?
I just Googled it. I have the FE one though.
Okay. Well, here, I'll pull up the FE one and you can just trust me, I guess. Or ideally, let's see. I think the FE one, let's see, resources, FE, fluids equations. It's the last page. You know that much. Yeah, and I don't really.
It's in feet on the FE.
Okay, so we'll look at that one. All right, so the way we're going to do this here, I need you to look at this while we're doing this, because I'm not going to be able to display this. It's just a curse of, you know, that's going to be a limitation of this format of lecturing. Okay, so I guess this will be the only Moody we're going to do today because we only have so much time. All right, so okay, here I'm gonna use the screen here, and I'm gonna describe what we're looking at, because I'm not gonna be able to do this without a. I mean, this is why I have designed lectures for this, because I can actually, you know, insert a Moody diagram. But I do really highly recommend. So really, I really highly recommend that you A, watch that video, and B, work on like playing with Moody a little bit. Okay, let's leave that number because we're going to need that. Okay. All right, my Rocky dog, how are you? You excited about the Moody diagram? All right, so, F, this friction factor depends on a few things. Hey, Rocky dog, we're almost at the end here. My oatmeal cold. I know you want to go outside, but you have to wait like 15 minutes, 10 minutes, 10 minutes. Can we agree? All right. All right, so this F, to get this F, it depends on, well, it depends on what range of the chart you're in, but it depends on two things, okay? It depends on Reynolds number, and it depends on what's called the relative roughness, okay? And different books will have different nomenclatures for the relative roughness. But let's go ahead and calculate one of these first. We're going to calculate the Reynolds number, which is why I put calculating this off until the end. But the Reynolds number is the velocity times the diameter over the velocity times the diameter over the viscosity. So we can plug that into a calculator fairly quickly. So the velocity is 25 point, well, we don't need all those significant digits. It's 26 feet per second, okay? And the diameter is 1. And the viscosity of the fluid, you know, I'm forgetting, it's 10 to the minus 6, I think, in the English units. Let's see real quick. So you're taking a test on the internet, so you could just have the viscosity table raised before you even start. And I can see which ones I've clicked on, which is always kind of nice. Cookie settings, we're gonna accept cookies. And actual cookies. Let's see here. Oh, engineering toolbox is usually the one I like to go to. And you go down here and we're looking for the viscosity. We're looking for the kinematic viscosity. And it's 10 to the minus 5. Well, okay. So technically, if you look it up, for 50 degrees water, it's 1.4 times 10 to the 5th feet squared per second. 1.4 times 10 to the minus 5th feet squared per second. Okay, now I don't usually bother with that 1.4. I usually just do 10 to the minus 5 because this ends up being nowhere near, like, there's nothing really I can do about all those extra significant digits. But if you want to use 1.4, that's fine. So we'll do 26 divided by 10 to the negative 5th, or well, I guess we'll do divided by 1.4. 10 to the negative 6th, 10 to the negative 5th, excuse me. And we'll get some really massive number like 1.9. How did that happen? 26 divided by 10 to the minus 5th. And I got a number to 10 to the 7th. I guess that makes sense. Okay. Okay, so this number is quite large. As you can see. Are you looking at Moody?
Yeah, got it. Got to pull it
Okay.
up.
All right. So when you have Moody, hold on, I think I've now opened it like 5 times. I keep scrolling, having to scroll all the way down. When you look at Moody, what we're gonna, oh yeah, so you can see the Reynolds numbers on the bottom. Okay, and this is a logarithmic scale, so that's a little bit annoying, but it's kind of nice. You see how I've written this is 1.9 times 10 to the 7th. So when you look at those Reynolds numbers on the bottom there, you can find 10 to the 6th. And you keep going to the right, you'll find 10 to the 7th. And then you'll see that it goes 2, 3, like the 3 is not marked, 4, 6, 8, 10, or whatever. So really, so this 1.9 times 10 to the 6th is basically 2 times 10 to the 6th, okay? Or 10 to the 7th, excuse me. So, I mean, you can't see where my mouse is, but it's somewhere way off to the right-hand side of the thing. So hopefully there's a few things you need to notice right there. One, if I'd put more significant digits into my calculation for Reynolds number, it wouldn't matter, right? If somehow instead of this being 1.9, it was actually 1.8 or it was 2.0, it wouldn't make any difference. I can't tell the difference. Okay, the other thing that's really interesting is that when you're way off on the right-hand side of this graph, if you look at all the dark black lines, that's what we're going to be reading in a second. Notice that they're all horizontal during this portion of the graph. So if your turbulence is high enough, then you get what we call complete turbulent or wholly turbulent, wholly spelled WHOLLY. And you basically, it's so turbulent that making it more turbulent isn't going to affect the friction in the pipe. It's basically so turbulent that you can't get more turbulent. I mean, you could add more energy, but it's not really going to affect, you know, how frictional the environment is. It's sufficiently turbulent, or, you know, whatever the word might be. Wholly turbulent is what they say. Okay, so in that area of the pipe, the only thing that's going to determine our friction factor, our friction factor is this relative roughness, which on this chart, they write as epsilon over D. This is a pretty common way to do it. So switch back to the other screen where you can see what I'm writing. Okay, because we have to get this epsilon over D. And that epsilon over D, this epsilon refers to, like, if you look at a pipe and you've got like roughness elements of the pipe, and there's a diameter here. Okay, and then there's, so the D is the diameter of the pipe, and the epsilon is some length scale that tells you something about how big those roughness things are. So if it's concrete, it might have really big roughness elements, you know, and if it's like glass, those roughness elements might be non-existent. Okay, so this is the roughness of the pipe, and this is the diameter of the pipe. So in this case, the diameter of the pipe is 1 foot, and this roughness is what we don't know. But if we knew what roughness it was, we could look at that chart on the Moody diagram, and we could find it. Okay, so what we're going to do now is all this making sense?
Yeah, I got you. And so then we're going to go with that 0.025 and find the epsilon, right?
So we'll start at 0.025. Where is that? It looks like 1, 2, 3, 4, 5. So I guess so it's somewhere between the second and the third line. And we're just going to trace it over to the right. And everything to the right is flat. So it looks to me like it's going to come in there at about like somewhere between the 0.002 and the 0.004, but closer to the 0.002. So what, like maybe 0.0025 or something? You know, all these problems, there is a certain, guesswork that goes into it. So I'm going to guess that the relative roughness is something like 0.0025. So then, yeah, we're just going to go look at, so if we plug that 0.0025 as a relative roughness, we multiply it by feet, by 1 foot to get the epsilon, we'll get 0.0025 feet, which, what does that look like? That probably is.
Concrete?
Yeah, well, no, it's rougher than concrete, isn't it? Oh yeah,
Since it
You're
goes
right.
from point.
It could be concrete. You're right. Could be concrete. You're right. So probably concrete. So we'll go with concrete. You're absolutely right. Okay, so it's a little bit, guesswork or whatever, but that's how it works. But the nice thing about this problem is it introduces you to this Moody diagram without actually having to solve the Moody diagram. Because what you're going to see in a second is that we're going to have to start iterating on this Moody diagram. Because sometimes you want to solve for, say, the diameter in a pipe. It's a what do you call it? A design problem. And it's like, what diameter pipe should we use? Well, the problem is the friction factor depends on the relative roughness and the Reynolds number. And both of those depend on the diameter. So you can't solve for the diameter without the friction factor, but you can't solve for the friction factor without the relative roughness and the Reynolds number, neither of which you can get without the diameter. So this is like a circular logic problem. And we basically have to iterate in order to get our solution. And so we'll talk about that next time. We'll start working some Moody problems next time. Anyway, any questions?
No, sounds good. I will watch the lecture before the next one, I promise.
Yeah, you don't have to promise me. It's entirely up to you. I'm happy to teach you either way. In this case, it will be good to see the Moody. And what I recommend is print out a Moody that you like and have that with you for the next lecture because it'll help. It's always good, especially with the Moody. I have students who don't really 100% realize that they don't know how to read the Moody until they get to the exam. And it's just like throwing points away. It's silly. It's a complicated diagram. It's not that hard, but it is very hard if you haven't figured it out yet. So anyway, cool. Well, good to see you. Bull, are you still with us? Bull is gone. Okay, well then, well, good to see you, Bull, if you watch this video, and good to see you, Paul, and I'll talk to you later.
All right, have a good one.
All right, you too. All right, bye.